This webinar is hosted by the Canadian Institute for Cybersecurity at the University of New Brunswick. Today's presenter is Samaneh Mahdavifar. She is currently a PhD student in computer science at the Canadian Institute for Cybersecurity. Samaneh has been involved with several industrial projects at CIC, including, but not limited to, user behavior profiling, device profiling, risk assessment, and risk mitigation plan. Today she will present on application of deep learning in malware detection and classification.
Thank you very much for registering in this webinar. As Mary Jo already said, I will talk about application of deep learning in malware detection and classification. First, I will give an overview to artificial neural network, and then we'll go through the basic deep network architectures. Then we will go through those studies and those papers that have used deep networks to detect malware, and then we'll discuss the challenges and limitations of the study, and then I will present concluding remarks, and at the end we will have question and answers. So first, we should start from what is an artificial neural network, because deep learning is based on artificial neural network. Most of the computers are very great at solving algorithmic and mathematical problems, but sometimes it's very difficult to define a real-world problem mathematically. For example, face recognition is difficult to define mathematically, but our brain can recognize a face or an image at once, and we don't know actually what's going on inside the brain. Artificial neural networks model information like the brain does. So first we should start from the brain. Here is a picture of our brain. Actually, human brain is an extremely large interconnected networks of approximately 10 to the power 11 neurons. And we can see here are neurons, and this is a neuron cell body. Each biological neuron consists of a cell body, as I said, a collection of dendrites that brings electrochemical information to the cell, and it outputs and transmits some electrochemical information out of the cell using an axon. Actually, neuron produces an output based on the summation of the input signals. But we are more interested in the artificial model of the neuron. The artificial model of a neuron is called Perceptron, which was developed in 1958 by Frank Rosenblatt in Cornell Laboratories. And it was the first linear classifier, or we can say first machine learning algorithm. As we can see here, a perceptron has some inputs, x1, x2, x3, and some weights, and it outputs based on an activation function that decides what would be the output, whether it fires or not, based on the weighted summation of the inputs. And the weight vector defines a hyperplane that acts as a classifier. It classifies the positive and negative samples. And Perceptron is working based on a learning rule, and it is very simple. That it includes some iterative updates, the weight vector. So it takes an input like xj and a desired output tj, and it computes the actual output, which is yj, and it updates the weights based on the following rule. And later we'll call it is a delta rule, and it updates the weights vector iteratively. So here we have assumed that we have I features, and xji is the ith feature of xj input. But Perceptron itself has a limitation, a very important limitation, that it only converges if data is linearly separable. So we cannot use it in all of the problems. For example, XOR problem is one of the simplest problems that cannot be solved by Perceptron. Here in this figure, we can see that there isn't a linear, we cannot find any linear decision boundary to classify these samples. Yeah, so that's why the scientists develop multi-layer perceptrons or feed-forward neural network. That's a perceptron is a building block of these networks, and it works based on supervised layering with backpropagation. And they have an activation function, and they work by summing the weights, actually the multiplication of the weights and the activations, and adding the bias, the red circles or the red nodes are biases. And the output actually decides whether, for example, the input is positive or negative. So it's a classifier, but it can distinguish data that is not linearly separable. So simply each layer weights the decision from the previous layer, and some complex and we can say abstract decision making occurs at higher layers. But without a nonlinear activation function in the network, the previous activation function, as we saw in Perceptron, was a linear activation function. Without the nonlinear activation function in the network, a neural network, I mean, no matter how many layers it has, would behave just like a single layer perceptron. So actually adding, and summing all of these layers would give you just another linear function. So that's why we introduce nonlinear function, and we use nonlinear function in deep networks, actually. Here are some examples of nonlinear activation function like sigmoid, tangent hyperbolic, and rectify linear unit or ReLU. So the algorithm that is used in neural network for fine-tuning the weights and parameters is called backpropagation. The basic strategy of the backpropagation algorithm is that it backpropagates the errors, and it uses the gradient descent error to update all of the weights and optimize a loss function. For example, a mean squared error is a type of loss function. We can define more sophisticated loss functions, and then update the weights based on these the gradient values of the weights. So first, we have a forward propagation of the training patterns input, and then the backward propagation of the output to compute the deltas. And for each weight, we multiply the output delta that I described in the perceptron rule, and input activation to get the gradient, and subtract the percentage of the gradient from the weights. And this percentage actually is defined by the learning rate. So the minimization is done using gradient descent algorithm, which is an optimization algorithm. But what is gradient descent? Here I have a contour plot of the error function, and it is plotted based on some parameters, for example, weights and biases. Here is actually the optimum minimum that you want to find. We want to minimize the whole error function. It works based on the iterative update of the parameters. And the formula is here. We compute the gradients of the weights, and this is the learning rate, and it's multiplied, and the weights are updated according to the gradient. The most, we can say, standard one of the gradient descent algorithm is batch gradient descent, but we have stochastic gradient descent and mini batch. In batch gradient descent, all training samples are required for a single weight update. But for example, in the stochastic gradient descent, one training sample is required, and we change the parameters to fit just one training example, so it's much faster. And in mini batch, we use B samples, for example, in each iteration instead of the whole training samples. As I said, gradient descent is the most basic algorithm, optimization algorithm, but we have a lot more. And there is another algorithm, momentum, gradient descent with momentum, that works faster than the standard gradient descent algorithm. Actually, it is based on the exponentially weighted average concept. In exponentially weighted average, actually we are looking into not only, for example, if theta here is the temperature of a city at time t, we are not looking at the current temperature, but also the temperature of previous days. So instead of these oscillations in the function, we will have a more smooth function. Here we can see, for example, this is a contour plot of the error function, and it is based on the weights and the parameters. The problem here is that with the gradient descent algorithm is that when we are using small learning rates, you can see we have a lot of oscillations towards the minimum. If we have larger or learning rates, we might overshoot the minimum, so we will never get to the minimum. So on the vertical axis, we can say in this way that in the vertical axis, we want slow learning, but in the horizontal axis, we want a faster learning. We want to get rid of these oscillations. So that's why we have used exponentially weighted average and gradient descent with momentum. And it's great in gradient descent with momentum, we compute exponentially weighted average of gradients. So we have gradients, but we first compute the exponentially weighted average of the gradients, and we use these gradients to update our weights. And these are the learning rates. So it is much faster algorithm, and there are lots of variations of gradient descent other than gradient descent in momentum, like AdaGrad and Adam optimization algorithm, RMS prop, but we'll not have enough time to dig into these algorithms. What are the basic deep learning architectures? So as I said, the deep learning is based on neural network. Although the first works of neural network dates back to 1950s and 1960s, but it was not sooner than 2006 that deep learning emerged as what we perceive today by Hinton's work, that he invented deep belief network based on RBM that I will explain later. So today, deep learning is used in every application, almost every application, like image recognition, speech recognition so far. And the goal of the deep learning algorithm is to produce high-level and flexible features from the raw input data that helps generalization in the classification. Here I introduce some of the basic deep learning and deep network architectures. The first one is autoencoder. Autoencoder is a type of neural network that is used to learn an efficient data encoding in an unsupervised manner. And we can see here, for example, here is an autoencoder, and first I try to map the input, an encoded version, like Z, and then I decode that to X prime. So I have X and a reconstruction of X, or another representation of X that is called X prime, and I try to minimize this reconstruction error. Accordingly, the weights and the other parameters are fine-tuned. And I have restricted Boltzman machine, which is a generative neural network that learns a probability distribution over input data, and it uses contrastive divergence in its training procedure. It has positive phase that it clamps X to H, which is hidden representation we can see of the input, and we have negative phase that maps H to X prime, and X prime is propagated again to the network, and we will have H prime, and there is another weight update procedure to update the parameters. And based on these basic building blocks, we have stacked autoencoders that we stack different autoencoders in a way that input layer of first autoencoder becomes the input layer for the whole network, and the hidden layer of, for example, the first encoder becomes the input layer to the next autoencoder. And the deep belief network is constructed by stacking restricted Boltzmann machines, so that, for example, here we have an RBM. And for the next RBM, the hidden layer of the first RBM becomes the visible layer of the next RBM, and so on. At the top, we have output layer. Another state-of-the-art deep network architecture is convolutional neural network, or CNN. it is very much used in feature recognition or image recognition, and it is based on the concepts of filters, and we apply filters to, for example, the inputs and different layers, and the results of a filter applied to the image is called a feature map. And we have different operations in CNN convolution, pooling that tries to reduce the dimensionality of the feature vector, and a fully connected layer. And we have recurrent neural network that's used in natural language processing. And the output of a neuron is not just dependent on the current state, but on the previous state of the neuron. In other words, we can say that they have a memory. And they are used, as I said, in speech recognition tasks very much. Okay, we talked about basic deep learning architectures, but here we want to know how we can apply them to malware detection problem. And we see a lot of studies have been done and how they have used these deep networks for detecting or classifying malware. Most of you know malware is a malicious software, and actually malicious software is any software that intentionally is designed to cause damage to computers or disrupt the computer networks, or it wants to steal information and data. So they have different objectives, but it can take the form of different forms like executable code, scripts, and for example, active contents, and they have different categories. For example, whether they can be virus or worm or Trojan or ransomware, and many other types. Depending on the infrastructure, the device or operating system that they are active and implemented on, we can have PC-based or Android-based malware. Whether you want to, if we want to identify a malware, we can have any of these tasks. Whether we want to detect a malware, we want to know whether a malware is malicious or benign, or whether we want to classify it into different categories, for example, Trojans, ransomware, virus, or adware, or we want to characterize it, dig into the families. Here, I have a graph that shows the breakdown of top 10 malware families, which was reported in January 2018 by CIS, and this is based on their activities. And for example, Coulter is we can say the top one, Emotet, CoinMiner, Nanocore. These are in January 2018 were the most active malware. And if you want to analyze a malware, there are different ways, whether it is static or dynamic. In a static analysis, we inspect an application's manifest, or we can disassemble the code and we extract the features. And one of the disadvantages of these approaches is that they can be defeated by malware, for example, obfuscation, and or malware repackaging. And dynamic analysis in another way, it means that we run the malware and see how it behaves, and then we can extract the features from the logs, for example, they produce, and most of the time they are run in a sandbox or emulated environments. And when we get the benefits of both methods, we have the hybrid methods. But why do we need deep learning for malware detection? As all we know, malware threatens the confidentiality and integrity of the data, which is communicated over internet. We know that we already have a lot of antivirus companies like McAfee, like Invincia, but most of them normally use signature-based methods. So the disadvantage of these signature methods is they are unable to identify zero-day malwares, which are mostly obfuscated or repackaged. And every day, the hackers and the bad guys are getting more professional and produce more sophisticated malware using obfuscation techniques and different techniques. So honestly, the malware detectors and the researchers are always far behind them, trying to catch them. So we really need an intelligent malware detection approach, and deep learning can help us here. Why? Because deep learning as we have already seen, can produce high-level abstraction of complex data. And one of the most important features of deep learning is that it has automatic feature learning. So it means that when a new malware type emerges, you don't need to hire a lot of engineers to extract the features from scratch, but you can learn the features automatically. So you save a lot of time and money. Here I have a taxonomy of deep network architectures and what deep networks have been used for malware detection so far based on the study that I had. And we can see that deep neural network or feedforward neural network, deep belief network, and CNN were the most popular one. But still, there are a lot of architectures and recurrent neural network also. For example, stack denoising or long short-term memory, that is a type of RNN, that have not been used that much. So I have a table of all the studies here. Very briefly, I go through all of them, of course not all of them, the most important ones, and they're based on the focus area features that they have used and a data set. Most of them are focusing on malware detection, not categorization or classification. We can say that Android malware and PC malware are, both of them have been investigated, and most of the features that have been used in the deep network architectures were API calls, system calls. Some of them have used permissions, and the data sets are very varied, and some of them are very big, millions, and some of them are very small, for example, just 400 samples or 600 samples. But I do not have enough time to go through all of these approaches, but I selected a few of them to just go into and see how they have applied deep networks to detect or classify malware. One of the first work is from Deep Hollow. In their work, they wanted to investigate how high-level and low-level features in malware detection affects the output or performance. So their focus area here is static malware detection, and it's PC-based malware. The features that they have used is high level, of course, because they wanted to compare their low-level features with the high-level ones from previous work. So their high-level features are p-import and metadata histogram, as you can see here, and bytes or entropy and the string histogram. There were 1024 input feature vector, but the one that they had extracted, it was extracted through static analysis from headers of a portable executable file, and the length was 636 input feature vector, and they had used DOS header, file header, optional header, and section header. The deep model that they had used was a stack denoising autoencoder, as you can see from the figure. So they have a corrupted input here. So they add noise to the input, and then they have the simple autoencoder. And they have two-phase training, first unsupervised pre-training and then fine-tuning. They have 5 layers, and they have used Adam optimizer and a stratified 5-fold validation. And the benchmark that they want to compare with is a feedforward neural network with 4 layers and sigmoid and parametric ReLU function. They have used dropout, and the data set contains 12,000 malware samples from virus share and 11,874 benign samples. What they have concluded is that when we are using high-level or optimal set of features, the adoption of a deep neural network does not significantly influence the performance. And another work integrates the convolutional neural network and recurrent neural network, and their focus area is on dynamic malware family classification. So they want to classify the malware samples. They have run the samples in a cuckoo sandbox, and the features that they have extracted is system call sequences. So they remove repeated system calls, and they use one-hot encoding for each unique system call. And the deep model is, as I said, a combination of CNN and RNN. They convolve 3 grams of the instructions, and they use 3-fold cross-validation. Also, they have max pooling. Their dataset are samples from virus share, Maltrieve, and private collections. The next one doesn't use API calls, but the blocks of API calls. So they categorize those API calls that are from the same library, and they focus on static Android malware detection. So they don't classify or categorize the malware. And their deep model is a deep belief network based on a stacked restricted Boltzman machine, and two-phase training, the pre-training and fine-tuning, as I said previously. And tenfold cross-validation is used. Their dataset is from Commodore Cloud Security, about 50,000 samples. The next one is Maldozer one. And one thing about the previous approach is that using this approach, they had an improvement of about 2.5% over SVM, 3% over ANN, and 16.5% over NB. I mean, naive base. And of course, 2.5% improvement over decision tree. The reason why I said about these figures is that it seems that API blocks are more meaningful than the API call sequences based on the figures that they have reported. And the last one is Maldozer, which is and static Android malware detection and characterization or attribution framework, and their features is based on API method calls, which is sequence of word embedding vectors. They haven't used sequences of one hot vector, but word embedding vectors that they had extracted using word2vec, because they wanted to have vectors of smaller sizes. One hot vector becomes very large vector. So they have used word embedding algorithms. And the deep model is a convolutional neural network with a convolutional layer and ReLU activation function and a max pooling layer and fully connected layer and an output layer that, for example, if it is used for detection, it has 1 neuron, and if it is for attribution, it has 10 neurons. Based on the number of the families. And they have used k-fold cross-validation. The k has been fine-tuned. And the dataset size is fairly big, 33K malware samples from 32 malware families from different sources, Malgenome, Drebin, and Maldozer. But the dataset is not that much updated. Most of them are from 2010 to 2012, and when running an unknown sample, their approach is not working that much well. Their F1 score is at most 70% on 2016 dataset, and they have about 60 to 80% F1 score for the samples between 2010 to 2012. So their approach is not working well on unknown malware samples. I will talk about the challenges and limitations, some of them, of the proposed methods. From deep learning wise, most of them haven't fine-tuned the parameters and optimized them. For example, number of the hidden layers, number of hidden neurons in each layers, and so on. And they haven't evaluated their framework very well. They have not calculated enough machine learning measures like accuracy, false positive, false negative. We should have all of them if we want to show that our approach is really working well. And there is normally no time complexity analysis. They haven't verified why they have chosen these specific deep learning approach, because some of the deep network architectures are good for some specific applications and so on. And one of the most important one is that they haven't explained the logic behind the decision that they have made. So they have seen neural network as a black box. So, of course, it is one of the critiques with neural networks, that they cannot explain the logic behind the decision that they make. And from a malware detection side, the dataset is mostly not up to date, or they have small size samples, not having diverse samples or malware families, so it will lead to overfitting problems. And whether they have either they have worked on static or dynamic analysis. So the hybrid analysis haven't been addressed that much, or mostly focuses on detection rather than classification. And at the end, I want to conclude. Deep learning today is mostly supervised, but the major drawback of supervised learning is that it requires a lot of labeled samples. So collecting labeled samples is very challenging. So we expect that deep learning be more unsupervised or semi-supervised. It means that we incorporate a little instruction or label data, and at the end, we have a lot of unlabeled data. And the two-phase training for parameter initialization, it means we can have unsupervised pre-training. Some of them have used in their approaches. It could assist us in assigning the initial weights and biases. And one of the problems of the deep network is that it might lead to overfitting problem. But dropout is an operator that can be used. It means that we free some of the neurons to let other neurons decide. And self-organizing neural network could be another alternative for layer fine-tuning. And another important point is that deep learning is not required to be used in all of the domains. So we should use deep learning in those domains that we need to learn nonlinear, complex hypotheses with a lot of features. So when we have a lot of features with or domains with larger scale data, deep learning is very recommended to be used. But in linear problems that we have small amounts of data, so SVM or other shallow learning algorithms could be used. And high-level features do not influence the performance of deep network architectures remarkably. This is a very important conclusion that we can make. So it is very highly recommended that we use deep learning in domains that we have raw data. So we don't need to pre-process the data that much. So that is the main goal of using deep network. So that works on the raw data. So if we process the data and then feed it in deep network, so it doesn't have that much value. And at the end, we can combine different types of data sources, for example, in malware samples, system calls, API calls, and for example, permissions, static features from the static analysis and features from the dynamic analysis to improve the results. That is one of the, I can say, the open problems, that how we can use all of these data sources in one simple feature vector and feed it into deep networks. Yeah, I'm waiting for your questions, or you can email me your question. I can answer that later.